In this video, we discuss about soil stabilization methods. What is soil stabilization? It is the process of improving the engineering properties of the soil for making it more stable. Soil stabilization is the process of improving the engineering properties of the soil for making it more stable. Then, when it is required? It is required when the soil available for construction is not suitable for the intended purpose. When the soil available for the construction is not suitable for the intended purpose, then soil stabilization is required. Soil stabilization alters the soil material itself for the improvement of its properties. So soil stabilization alters the soil material itself. For what? For improving its properties. It is used to reduce the permeability and compressibility of the soil mass in earth structures. It is used to increase the shear strength of the soil. Soil stabilization is also required to increase the bearing capacity of the foundation soils. The next is types of soil stabilization. The first type is mechanical stabilization. The next is cement stabilization. Third one is lime stabilization. Then bituminous stabilization, and finally chemical stabilization. Then what is mechanical stabilization? It is the process of improving the properties of the soil by changing its gradation. Two or more types of natural soils are mixed to obtain a composite material. That material will be superior to any of its components. That is, the resulting material has superior quality than the components mixed. To achieve desired grading, sometimes the soil with coarse particles are added or the soils with fine particles are removed. So coarse particles can be added or fine particles can be removed to get desired grading. Mechanical stabilization is also known as granular stabilization. For the purpose of mechanical stabilization, soils are subdivided into two categories. First one is aggregates and second one is binders. Aggregates means the particles of size larger than 75 micron, and binders means the particles of size smaller than 75 micron. Proper blending of aggregates and binders is done in order to achieve required gradation of the mixed soil. That is, the aggregates and binders should be properly blended. Their proper blending is required to achieve the required gradation. So then, after the mechanical stabilization, the mechanical stability of the mixed soil depends on certain factors. The factors are mechanical strength of the aggregate, mineral composition, gradation, plasticity characteristics, and compaction. The first factor that affects the mechanical stability is the mechanical strength of the aggregate. The mixed soil is stable if the aggregates used have high strength. If the aggregates have high strength, then the soil will be stable. If the mixture is properly designed and compacted, even if the aggregates of relatively low strength can provide good mechanical stability. even if the aggregates is of low strength. If the mixture is properly designed and compacted, then we get good mechanical stability. Then second factor is mineral composition. The mechanical stability of the mixed soil depends upon the composition of the minerals in it. Minerals should be weather resistant, and there are certain materials such as sodium sulfate and sodium carbonates that affects the stability. That is, this sodium sulfates and sodium carbonates cause large volume changes. This volume change causes due to the hydration and dehydration of these materials. These are detrimental to the stability. That is, it affects the stability. And the third factor is gradation. The gradation of the mixed soil should be such that the voids of the coarser particles are filled with finer particles so that a high density is obtained. The voids of the coarser particles is filled by finer particles, so high density is obtained, thereby we get proper gradation. Next factor that affects mechanical stability is plasticity characteristics. Plasticity characteristics is different for surface soil and base courses. For the soils used for surfacing, the liquid limit should be high and plasticity index should be high, because to attain better moisture retention capacity and greater cohesion, the plasticity characteristics should be high. Liquid limit should be high, plasticity index should be high. So this helps to provide a better seal against the downward movement of the surface water. That is, surface water retain in that layer itself. Then in the case of base courses, plasticity characteristics is different from the surface soil. Soil in base courses should have low plasticity. That is, to avoid excessive accumulation of water and the resulting loss of strength. The next factor is compaction. Mechanical stability of the stabilized mass depends upon the degree of compaction attained in the field. Normally, the compaction is done at or near the optimum moisture content. So, the factors is over. The mechanical stabilization is the simplest method of soil stabilization. It is generally used to improve the subgrades of low bearing capacity. That means bearing capacity can be increased by mechanical stabilization. This method is extensively used in the construction of bases, sub-bases, and surfacing of roads. Next, we discuss about cement stabilization. It is the process of mixing pulverized soil and Portland cement with water and compacting the mix. Pulverization means the crushing of soil to fine powder by mechanical means. So, the soil is crushed into fine particles of size less than 5 mm. that pulverized soil and Portland cement is together mixed with water and it is compacted to attain a strong material. The material obtained by mixing soil and cement is known as soil cement. Soil cement becomes a hard and durable structural material. Then next is types of soil cement. Mainly there are three types of soil cement. They are normal soil cement, plastic soil cement and cement modified soil. The first one is normal soil cement. It consists of 5 to 14% of cement by volume. The quantity of cement mixed with soil is sufficient to produce a hard and durable construction material. The quantity of water used should be just sufficient to satisfy the hydration requirements of the cement and to make the mixture workable. What is the meaning of hydration? Hydration is a chemical reaction in which major compounds in cement form chemical bonds with water molecules and becomes hydrates or hydration products. Approximation for every kilogram of cement, that is for every kilogram of cement about 0.35 kilogram of water is needed to fully complete hydration reaction. For every kilogram of cement about 0.35 kilogram of water is needed to fully complete hydration reaction. So water is added in such a way that it satisfies the hydration requirements. Normal soil cement is quite weather resistant and strong. It is commonly used for stabilizing sandy and other low plasticity soils. The second type of soil cement is plastic soil cement. It also contains cement of 5 to 14% by volume. But the difference is that it has more quantity of water to have wet consistency similar to that of plastering mortar at the time of replacement. Plastic soil cement can be placed on steep or irregular slopes. It can be used for waterproofing lining of canals and reservoirs. Then third type of soil cement is cement modified soil. It is a type of soil cement that contains less than 5% of cement by volume. It is a semi-hardened product of soil and cement. It is quite inferior to the other two types. That means its quality is less than the other two types. As the quantity of cement used is small, it is not able to bind all the soil particles into a coherent mass. It can reduce the swelling characteristics of the soil. The use of cement modified soil is limited. The next is factors affecting cement stabilization. They are type of soil, quantity of cement, quantity of water, mixing, compaction and curing, and admixture. Next is construction methods of cement stabilization. There are two types of construction methods. They are mix-in-place method and central plant method. Mix-in-place method is similar to agriculture rotary cultivator. First, the soil is pulverized. Then, dry cement is spread over the soil. After that, water is sprinkled in layers. Then again it is remixed and shaped to camber. And finally it is compacted using rollers. The next construction method is central plant method. In central plant method, the construction is faster and expensive. That is, the construction is faster but it is expensive when compared to the mix-in-place method. In this method, the excavated soil is transported to a plant located at a suitable place. Then, required quantity of cement is added to the soil in the plant. The mixed material is then discharged into dumper trucks and transported back to the subgrade. It is spread and properly compacted. The figure shows cement stabilization. It shows spreading cement ahead of the machine and injection of water. In figure, we can see a milling and a mixing drum. A microprocessor controlled pump is used for spraying water. The treated materials and untreated materials are separately shown in the figure. This figure shows the soil mixed with cement. This figure shows the compaction of the soil cement using suitable equipment. This figure shows the resulting cement stabilized soil. Next type of soil stabilization is lime stabilization. Lime stabilization is done by adding lime to a soil. It is useful for stabilization of clay soils. When lime reacts with soil, there is exchange of cations in the adsorbed water layer and a decrease in plasticity of the soil occurs. The resulting material is more friable than the original clay, and therefore it is more suitable as subgrade. How lime is produced? Lime is produced by burning of limestone in kilns. Quality of lime depends upon the parent material and the production process. The next is type of lime. Basically, there are 5 types of limes. First one is high calcium quicklime. Second is hydrated high calcium lime. Next is dolomitic lime. Then normal hydrated dolomitic lime. Fifth one, pressure hydrated dolomite lime. Quicklime is more effective as stabilizer than the hydrated lime, but hydrated lime is more safe and convenient to handle. Generally, hydrated lime is used. This hydrated lime is also known as slaked lime. The higher the magnesium content of the lime, less is affinity for water and the less is heat generated during mixing. Lime required for stabilization varies from 2 to 10% of the soil. Lime stabilization is not effective for sandy soils. When lime reacts with wet soil, it alters the nature of adsorbed layer by base exchange. Calcium ions replace the sodium or hydrogen ions. The double layer is usually depressed due to an increase in cation concentration. However, sometimes the double layer may expand due to high pH value of lime. Lime reacts chemically with available silica and alumino in salts. A natural cement composed of calcium alumino silicate complexes is formed, which causes a cementing action. This reaction depends upon the effective concentration of the reactants and temperature. The soil becomes more friable and workable. The strength of lime stabilized soil is generally improved. The next is construction methods. Construction methods used in lime stabilization are similar to those used in cement stabilization, but there are some differences. They are, as the reaction in the case of lime is slow, there is no maximum time limit between the addition of lime to the soil and the completion of compaction. Lime may be added in the form of slurry instead of dry powder. A rest period of 1 to 4 days is generally required after spreading lime over a heavy clay before final mixing is done. Before final mixing, a rest period of 1 to 4 days is required. The soil lime is compacted to the required maximum dry density. After compaction, the surface is kept moist for 7 days and then covered with a suitable wearing coat. This figure shows lime stabilization, and this figure shows lime stabilized soil. The soil before and after lime stabilization is shown in this figure. Next type of stabilization is bituminous stabilization. Any inorganic soil which can be mixed with asphalt is suitable for bituminous stabilization. In cohesionless soil, asphalt binds the soil particles together and serves as a binding agent. But in cohesive soil, asphalt protects the soil by plugging its voids and waterproofing it. It helps to maintain low moisture content and to increase bearing capacity. The amount of bitumen required varies between 4 to 7% by weight. The next is types of soil bitumen. First type is soil bitumen, that is proper. It is a waterproof cohesive soil system. The best results are obtained if the soil satisfies the following criteria. About 50% of soil should pass through 4.76 mmC. About 35 to 100% soil should pass through 0.425 mmC. About 10 to 50% soil should pass through 0.074 mmC. Plastic limit should be less than 18%. Liquid limit should be less than 40%. The maximum size of the particle should not be greater than 1/3 the compacted thickness of the soil bitumen. The quantity of bitumen required varies from 4 to 7% of the dry weight. Then second is sand bitumen. This is a bitumen stabilized cohesionless soil system. The sand should be free from vegetable matter or clay lumps. The sand require filler for mechanical stability. It should not contain more than 25% passing number 200 C material for dune sands and not more than 12% in case of other types of sand. Number 200 means 0.074 mmC. The amount of bitumen required varies from 4 to 10%. And the third type is waterproof clay concrete. Soil of good gradation is waterproofed by uniform distribution of 1 to 3% of bitumen in the soil system. Soils of 3 different gradations are recommended. For the 3 gradations, the percentage passing number 200. Number 200 means 0.074 mmC, varies between 8 to 12, 10 to 16, 13 to 30. The next is oiled earth. A soil surface consisting of silt layer is waterproofed by spraying bitumen in 2 or 3 applications. Slow or medium curing bitumen or emulsions are used. The bitumen penetrates only a short depth into the soil. The bitumen required is about 5 liters per square meter of soil surface. The next is factors affecting bituminous stabilization. The first factor is type of soil, then amount of asphalt, mixing and compaction. First factor is type of soil. It is effective in stabilizing sandy soils having little or no fines. Cohesive soil with plastic limit less than 20% and liquid limit less than 40% can be stabilized. Plastic clays cannot be properly treated because of mixing problems and large quantity of asphalt is required. Fine grained soils having high pH value and dissolved soils do not respond well. The next factor is amount of asphalt. The quality of stabilized soil improves with the amount of asphalt up to a certain limit. Up to a certain limit, when asphalt increases, the quality of stabilized soil also increases. Excessive asphalt results in highly fluid mixture that cannot be compacted. But when the asphalt becomes it becomes highly fluid mixture that cannot be compacted. The next is mixing. The quality of product improves with more thorough mixing. Mixing needs to be done thoroughly. The next factor is compaction. The dry unit weight of bitumen soil depends on the amount and type of compaction and the volatile content. In modified AASHO test, maximum dry density occurs at a volatile content of about 8%. AASHO test means American Association of State Highway and Transportation Officials. According to that test, maximum dry density occurs at a volatile content of about 8%. Next is construction methods. There are some points to be noted. The construction it is necessary to aerate the mix between mixing and compaction and between compaction and application. For high stability, layer method of construction is preferred. Each layer is about 5 cm thick. In mix-in-place method, the bitumen is sprayed in several passes. Each layer is partially mixed before the next pass. Climatic conditions influence the amount of bitumen that can be applied. The figure shows the soil stabilized with bitumen. The next is chemical stabilization. Soils are stabilized by adding different chemicals. Its main advantage is that setting and curing time can be controlled. The following chemicals have been successfully used. First one is calcium chloride, then sodium chloride, sodium silicate, polymers, chrome lignite and other chemicals. So first chemical is calcium chloride. It causes colloidal reaction and alters the characteristics of the soil. It is deliquescent and hygroscopic and reduces the loss of moisture. It reduces the chances of frost heave as the freezing point of water is lowered. Effective as dust calming. Effective for silty and clay soils which lose strength with an increase in water content. It causes a slight increase in maximum dry weight. It lowers the optimum water content. Causes a small decrease in strength of soil. However, if the compacted soil is put to water imbibitions, water pickup is reduced and the strength of soil increases. The benefits of the stabilization requires the presence of chemical in the pore fluid. As the chemical is leached out, the benefits are lost. Its performance depends on the groundwater movement. The construction methods are similar to those used for lime stabilization. Its quantity required is about 0.5% of the weight of the soil. The next chemical is sodium chloride. Its tendency for attraction of moisture is somewhat lesser than that of calcium chloride. So, tendency for attraction of moisture, that is less than that of calcium chloride. Crystallization in the pores of the soil, and it forms a dense hard mat with the stabilized surface. The pores in the soil filled up and retard further evaporation of water. It also checks the tendency for the formation of shrinkage cracks. It is mixed with soil either by mix in place method or plant mix method. It should not be applied directly to the surface. The quantity required is about 1% of the soil weight. Next chemical is sodium silicate. It is used as solution in water, that is also known as water glass. It is impervious. It is directly injected into the soil. It increases the strength of the soil and make it act as a dispersing agent. It increases the maximum compacted unit weight of the soil. The chemical required varied between 0.1 to 0.2% of the weight of the soil. This method is relatively inexpensive, but long-term stability is doubtful. The treated soil may lose strength when exposed to air or groundwater. Next is polymers. Polymers are long-chained molecules formed by polymerizing of certain organic chemicals called monomers. So, polymerizing of certain organic chemicals called monomers we get polymers. By polymerizing of monomers, we get polymers. They may be natural or synthetic. Resins are natural polymers. Calcium acrylate is commonly used synthetic polymer. When added to soil, reaction takes place. Sometimes catalyst is added with monomers to the soil. In that case, polymerization occurs along with the reaction. The next is chrome lignin. Lignin is obtained as a byproduct during the manufacture of paper. Chrome lignin is formed from black liquor in sulfide paper manufacture. Sodium bicarbonate or potassium bicarbonate is added to sulfide liquor to form chrome lignin. It slowly polymerizes into a brown gel. When added to the soil, it slowly reacts to cause binding of particle. Reaction takes place slowly and binding takes place. The quantity required varies from 5 to 20% by weight. As lignin is soluble in water, its stabilizing effect is not permanent. Then other chemicals. Waterproofers such as alkyl chlorosilanes, siliconates, amines and quaternary ammonium salts have been used for soil waterproofing. Coagulating chemicals such as calcium chloride and ferric chloride have been used to increase the electrical attraction and to form flocculated structure in order to improve the permeability of the soil. Dispersants such as sodium hexametaphosphate are used to increase electric repulsion and to cause dispersed structure. The compacted density of the soil is increased. Phosphoric acid combined with a wetting agent can be used for cohesive soils. It reacts with clay minerals and form an insoluble ammonium aluminium phosphate, insoluble aluminium phosphate. This figure shows the chemical stabilization of the soil. Thank you.